Okay, we will start the lesson today. Okay, Miss Amy, can you hear me? So we will start now. Okay, so the lesson that we are going to do today is going to be first. Okay, we are going to do a revision. Okay, on standard electrode potential, and then the second part of it is going to be our Nerst equation. Okay, so here, okay, if you look at what we have done, okay, in the previous lesson, okay, it is going to be, we discussed about standard electrode potential. Okay, so if you want to measure a standard electrode potential of a cell, okay, you need to compare that with a standard hydrogen electrode. So the standard hydrogen electrode, okay, you can see from here, this is the diagram. Okay, you need to know how to draw this diagram. And when we are talking about standard, so we need to follow all the standard conditions, 25 degrees Celsius, 1 atmosphere, okay, and then the concentration of ions must be in 1 mole per dm cube. Okay, so we call it as E standard. Yeah. Now, if you want to measure the standard electrode potentials, okay, using the hydrogen electrode, okay, using the hydrogen cell as a reference cell, there are 3 different setups that you need to know, okay, which is going to be, the first one is the metal-metal ion. Okay, we have done this, okay, non-metal and non-metal ion, and we have ion and ion. Okay, let's actually go through what we have learned in the previous lesson. So this is going to be a setup. Okay, you can see here. Okay, the one on the right hand side is going to be your reference, which is going to be your hydrogen cell. Okay, and then on the left hand side here is going to be, you can see copper rod and then copper ion. So you can see this is example of metal and metal ion half cell. Okay, and how it works and so on, you should know. Okay, but I am teaching you about, okay, how if you have a metal and metal ion, okay, how do we see that from the equation itself? Okay, do remember it must be under standard reduction form. Okay, reduction means the electron on the left. Yeah, you can see here you have copper 2 plus, which is going to be aqueous, and then copper is going to be metal. So we know that this is a metal with a metal ion. So we draw the setup to be like this. Okay, and then if you have non-metal and non-metal ion, so how do we draw? Okay, if you look over here on the right hand side, it's always going to be the same. So I'll just show you for both examples. Right hand side is going to be always the same. But now if let's say I want to measure for Cl2 and Cl minus. Okay, so Cl2 is non-metal, it's gas, and Cl minus is going to be aqueous. So what is this? This is non-metal and non-metal ion. So the non-metal is gas, so you need to put something similar to hydrogen over here. And then we are going to use the platinum. Okay, this one they call it platinum black. Yeah, so it comes into contact with the chlorine gas, and it comes into contact with the chloride ions over there. Yeah, and then there is salt bridge to connect both of the cell. Yeah, so this is going to be one example. Okay, if you have this going to be non-metal and non-metal ion. Okay, but sometimes you have a situation where, okay, you can have the iodine. Okay, if the iodine is going to be in solid. Okay, iodine is non-metal, it is solid. Okay, and then you see I minus is going to be aqueous. So you don't go and put, okay, something similar like set up to collect gas or something like that to put gas. No, iodine is solid. So therefore, okay, solid will be at the bottom, okay, and then you put the ion at the top. Yeah, so you make sure that the platinum wire, okay, is going to be coming into contact with both, okay, with both I minus and also I2 solid. Yeah, and then you draw. Okay, you draw. So this is an example of non-metal and non-metal ion. And let's move on to the third example. The third example is ion-ion. Now, for ion-ion, you can see one example here, Fe3 plus and Fe2 plus. Both of them are ions, aqueous. Yeah, you cannot separate them. You put them together. Okay, you put them together. So you put both of them together. You mix. Okay, you mix. But you need to be very, very careful. Yeah, you cannot just simply say MnO4, like for example, this example, MnO4, and then you have Mn2 plus. Always analyze, okay, always analyze, okay, when they give you an ion, let's say ask you to drop. First thing is to check the equation, okay, you check the equation, find out whether there is a presence of H plus. You can see here there is no presence of H plus. But if you go and look for this particular half cell, there is presence of H plus. If there is presence of H plus, do not forget, okay, I repeat again, do not forget about this H plus. You must put, okay, 1 mole per dm cube of H plus. Okay, it can be in form of HCl, it can be in form of H2SO4, up to you, HNO3, up to you. But make sure that they are going to be 3 aqueous solutions with the concentration of 1 mole per dm cube mixed together. Okay, so if you don't have the acid, what will happen? Okay, you won't have the reaction. Okay, you won't have the reaction, because in order for this reaction to happen, okay, you must have the acid. Okay, you must have the H plus. Okay, please remember that. Okay, now we have also learned about how to use the E standard. Okay, so standard cell potential can be calculated for 2 half cells, and I told you, look at this value, make sure the equations are in the reduction form, okay, where the electron is going to be on the left. You see all these are okay. Okay, first thing is you find out which one is more positive. So this is going to be more positive, therefore they will go to the right, and this one will go to the left. Okay, so if I want to rewrite it again, it's Ag plus electron to give me Ag. This is going to be plus 0.8. And this one, since it's going to the left, okay, I will write it as zinc, okay, to give you zinc 2 plus 2 electron. The moment, okay, the moment when we have, okay, the movement is going to go to the left, okay, what we need to do is, you need to change the sign to become opposite. Like for example, here is negative. Now you change it into positive 0.76. Okay. Now the final step is, okay, we want to eliminate the electron. So we always put 2, 2, and 2. Okay. But remember, do not go and times this by 2. Yeah. Only sign change. Okay. But you don't times the E value by 2. Okay, it's not the same if you compare with enthalpy changes. Yeah, so you add, okay, you add these two, what will happen? You are going to get 2 Ag plus zinc to give me 2 Ag plus zinc 2 plus. Okay, so what is going to be the E value? The E value is these two added together. You can see when you add together, the E value is positive 1.56. Okay, so you do think my connection. Okay, hold on. The next step, okay, is going to be, okay, you can see, okay, it's going to be 1.56 volt. Yeah, so these are the things that you must remember, okay, from this chapter. Yeah, so here, okay, if I go to this example, electrochemical cell, another example. Yeah, so if I want to rewrite this, similar. Yeah, you look at the positive. Yeah, this is going to be the most positive, it will go to the right. Yeah, this is going to be negative, it will go to the left. Okay, so if I want to write Cu2 plus 2 electron to give me copper, okay, 0.34. Okay, and then this one zinc, it is going to give me zinc 2 plus 2 electron. Since I changed the position of the equation, I change it into positive 0.76. Okay, I want to combine these two. Okay, no need to times, it's 2 electron. Okay, cancel. I will get Cu2 plus zinc. Okay, it's going to give me copper plus zinc 2 plus. When I add, okay, I just need to add these two, and I will get a positive 1.10 volt. Yeah, quite simple. Yeah, and from here you can also determine few things. Okay, what are the things that you can determine? Okay, you can find out which one will lose electron. You can see here the one that is going to the right, or you can see from here itself, copper 2 plus is receiving electron. Zinc is the one that is losing electron. So if zinc losing electron goes from the zinc terminal and it will go and enter the copper rod. Yeah. So zinc automatically is going to become a negative terminal. This is going to become automatically a positive terminal. Yeah. So you need to remember this as well. Okay. Now, if I move on, yeah, this is going to be extension to it. Okay, you can see here they are asking about the direction of electron flow. Okay, so if you look over here, okay, first thing I'm going to maybe show you only one example here, A. Okay, you can see F2 plus 2 electron to give you 2F. You refer to the data booklet. Okay, I have taken certain data over here. So this is going to be plus 287. Okay, this is going to be plus 287. And if I have this equation, okay, if I go and look for that equation, it's going to be negative 1.18. Okay, if I look from here, okay, and I want to know which one will go to the right, which one is going to go to the left, positive and negative. So of course, this is going to go to the right. It's going to be receiving electron. So this is going to go to left. So I know that Mn is losing electron. So if Mn is losing electron, I can tell the electron is moving from Mn, okay, to the other cell. So that's why you can see this is going to be the negative terminal. Okay, you can see here Mn2 plus and Mn is the half cell. Okay, that is going to be the negative pole. Okay, negative terminal. Okay, where the electron is going to flow from the Mn2 plus and Mn, it will go to the half cell that contains F2 and F minus. Yeah, so this is going to be how you determine. Okay, the same thing you can apply for all these examples. You can try on your own, okay, later. Yeah, so how to identify, okay, the movement of electrons, but something to always remember. When they ask you to indicate the direction of electron flow, always indicate the direction to be on the external circuit, which is your wire. Okay, this is going to be your wire. You don't go and indicate, okay, the electron is going to go here, then it will go here. Okay, don't do that. Okay, because, okay, if you just simply tell that, it means that, okay, always remember electron always flow, okay, in the external circuit. This one is going to be movement of ions. Okay, so if you want to show, it's okay if you just say from here to here, it's okay, fine. Okay, but it will be better if you can show like what I have shown you in the external wire over here. Okay, the direction that I've shown you. Okay, it's moving over here. Okay, now if I continue, okay, you can see here, okay, all this data, I think in the previous lesson note also is available, okay, where they have all this information given to you, okay, all these are given to you. I just put it over here. Now, we are going to look into predicting feasibility of the reaction. Yeah, predicting feasibility of the reaction is going to be very important. Okay, now, if you look at the way these things are arranged, you can see this is going to be hydrogen is always 0.00. Yeah, they have arranged this in form of, okay, the one that is more positive, okay, the E value, the E standard, the one that is more positive at the top. Okay, do remember in your data booklet, it's not arranged properly. Yeah, so you can see sometimes it's mixed. Okay, sometimes it's arranged properly, but doesn't matter. Okay, if you look over here, this is taken from your textbook. Okay, if you look over here, okay, you can see the one that is more positive is at the top. Okay, and the one that is negative is at the bottom. Yeah. Now, what is important over here is I will suggest you to memorize this. always remember the one at the top left as SOA. What is SOA? SOA is strong oxidizing agent. Okay, what is oxidizing agent? Oxidizing agent is something that will oxidize others, but they themselves will get reduced. So what is reduced? Reduced is gain of electron, right? So we know that, okay, at the top, it means the Cl2, okay, compared to all those, okay, that you have over here, okay, compared to all those, they have tendency, because more positive, they will have the tendency to go to the right. Okay, it means that Cl2 has the greatest tendency to gain electron or to be reduced. Or you can say Cl2 compared to all the other examples that you have over there, they are the strongest oxidizing agent. Yeah, you can actually remember that. And if this one is strongest oxidizing agent, of course, this one would be the other way around, strongest reducing agent. Okay, so this one I will teach you how to apply this, okay, because, okay, if you want to predict feasibility, okay, using the E value, okay, there are two methods, okay, there are two methods. Method number one, okay, using the table. Now, if you want to, okay, if you want to, let's say you see, yes, strongest oxidizing agent, okay, always remember, strongest oxidizing agent will always oxidize the one that is going to be this part, which is going to be the strongest reducing agent, okay? It means that, okay, just say that they are very good couples. Strongest oxidizing agent, okay, they will oxidize, okay, strongest reducing agent. Okay, always remember that. Okay, so it means that, okay, it means that as long that this is going to be a strong oxidizing agent and this one is going to be, the one over here is going to be strong reducing agent, they can react. It is feasible. So you can see here how I can use this method. This method is, remember, just now we have so many equations, but now I have only two equations. What is important is you rearrange first, okay? You don't identify which one is positive and negative earlier first, okay? You rearrange the E value, okay? The E value that is going to be the more positive, you arrange at the top. The one, the E value less positive, you arrange at the bottom a bit, yeah? And then according to the table just now, I told you this is going to be, so what? Strong oxidizing agent. And I know this is going to be SRA, strong reducing agent. Okay, it means that, okay, if I have a question, will Cl2, okay, oxidize, okay, Fe2 plus? Okay, my question is, can Cl2 oxidize Fe2 plus? Now, Cl2 is a strong oxidizing agent. Fe2 plus is a strong reducing agent. Can they react? The answer is yes. Okay, the answer is yes. Why? Because they are good couples. Why? Okay, because strong oxidizing agent, okay, will always try to oxidize, okay, strong reducing agents. Okay, quite easy to understand. Okay, so this is method number one. Yeah, method number one. It's too complicated. Then we go back to simple method. Yeah. Simple method is, okay, this simple method is going to be, they are asking, can bromine, Br2, okay, oxidize, okay, silver to silver ions. It means silver to become Ag plus. Can it happen? What I will suggest you to do is, okay, you write the equations, okay, Br2, okay, Br2, okay, plus 2 electron, it will give you Br2 Br minus. Okay, this one you must write in form of reduction first. Yeah, and then the second one you must write Ag and Ag plus. So it must be Ag plus electron to give me Ag. Okay, then you look at your data booklet. Okay, you look at the data booklet, get the values. Okay, get the values. So here you can see this Br2. Yeah, so this is going to be positive 1.07. And you can see for Ag plus, okay, you can see here, this is going to be 0.80, 0.80. What I need to do, just use whatever things that you have learned in the past with me. Yeah, you can see that, okay, this is going to be positive, this is going to be less positive. this is going to go to the right. Okay, this is going to go to the right, or this is going to go to the left. Okay, so if this one is happening, so if I will just write down, okay, so Br2, okay, plus 2 electron to give me 2 Br minus, so that's going to be plus 1.07. This one is going to the left, okay, so it's supposed to be Ag. It's going to give me Ag plus electron, okay, and this is going to be negative 0.80. I times by 2, doesn't matter, okay, doesn't matter, okay. When I add these two together, okay, I want to find out, okay, whether Br2, okay, my aim is to find out whether Br2 can change the silver to become 2 Br minus to become 2 Ag. Means I want to actually find out whether this thing can happen or not, okay. You can find out whether this thing can happen by identifying the E value. What is the E value? You add, okay, these two, okay. When you add, okay, when you have 1.07, okay, minus 0.80, when you do that, okay, if you have a positive value, okay, then the reaction is feasible. If you have a negative value, then the reaction is non-feasible. Okay, so this one is, okay, let's say if I calculate, then it's going to be 1.07, you minus with 0.8. And it's going to be a positive 0.27. Because this is positive, okay, because this is positive, therefore this can happen. Okay, this is going to be another method. Okay, another method. Now, if let's say we try, okay, let's try this, whatever method that you want to use, okay, up to you. Okay, checkpoint 1. So here, okay, will iodine oxidize silver to silver ions. Okay, so silver to silver ions. Okay, this is going to be, I'll just put Ag plus electron to give you Ag. Okay, that's going to be 0.80. Iodine, okay, let's write iodine, okay, plus 2 electron to give me 2I minus, okay. So iodine is here, 0.54. Let's try method number 1. Okay, method number 1. What is that method? Okay, that method is telling that, okay, iodine, okay, iodine. In this case, you can see, okay, you can see that, okay, the one, if I rearrange accordingly, you can see the one on top is actually 0.80. And this is going to be SOA, strong oxidizing agent. And this is going to be your SRA, strong reducing agent. If I use Ag plus, okay, Ag plus can oxidize I minus, but can iodine oxidize silver to silver ions? The answer is no. They are not SOA combination with SRA. Okay, if this one you couldn't understand, it's fine. I can understand. Let's say not everyone can understand every single thing. Okay, it doesn't matter. Okay, if you don't understand that, you just look at this. This is going to be a more positive value. This is going to go to the right. Okay, this is going to go to the left. Okay, so it's supposed to be Ag plus electron to give me Ag. Okay, and then, okay, it's supposed to be 2I minus. It's going to give me I2 plus 2 electron. This is going to be 0.80, and this is going to be negative 0.54. Okay, and if I add, it will be a positive value. Okay, it will be a positive value, but please take note about what are you adding first. Okay, what is the final equation? The equation is 2I minus plus 2Ag plus to give me 2Ag plus I2. It means that, okay, the reaction is positive, the E value is positive or feasible only if this is I minus changing into I2. But the question is, can iodine oxidize silver to silver ion? The answer is, okay, the answer is no. Okay, if it is going this way around, okay, you need to reverse the equation, which is going to be a negative value. Okay, so we do not want that. Okay, which is going to be, you can just come up with this conclusion. The answer is they will not oxidize silver to silver ions. Okay, there are two methods to use. Yeah. Now, So this is going to be another example. Okay, so I'll just show you for A. Okay, so can MnO4 ions oxidize? Okay, Cl minus to Cl2. Okay, so first go and find out the equation to be used. They have mentioned acidic condition, so make sure you select MnO4 minus in acidic condition. Okay, if you look over here, the one that is going to be in acidic condition is going to be not this, okay, not this, not this, okay, not this, okay. But you can see here, okay, under acidic condition, it can be this or this. Okay, it can be these two. Okay, because there's H plus. Now, then I want to look at Cl2. So this is the equation for Cl2. So now, okay, my question is, okay, can this reaction oxidize, okay, the Cl2, okay, Cl minus to Cl2. Now, I will use the first method, okay, you see here. This is 1.36, okay, so Cl2 plus 2 electron, 2 Cl minus. It means that, okay, if I want this to be oxidized, I must have something that is actually above, okay? It means something must be on top, SOA, okay? So 1.36, it must be something that is greater than 1.36, okay? So if it is greater than 1.36, it can be, you can see here, you can use this, okay? You can also use this, no problem. Okay, you can use them. Okay, and then, okay, if you want to write down, you can see, maybe I'll just write down, okay, this example. Okay, here, okay, you can see here, they have used the one that is going to be with Mn2 plus, okay, the one that will give you Mn2 plus. Okay, even, yeah, you can actually use any of these two. Okay, no problem. Okay, if you use that, okay, what will happen is you have 1.52 here. If I use 1.52, this one, yeah, if I'm using this one, okay, I will have MnO4 minus plus 8H plus 5 electron. Okay, you can write the equation. Okay, but what I can say is MnO4 minus, okay, can oxidize Cl minus. Why? Okay, this is SOA and this is SRA. Okay, and you can also use the E value. Okay, if you want to find out, yeah, E value, if you want to use, the simplest way that I use is, okay, they put MnO4 minus, can it oxidize? Okay, so if I want oxidize, okay, it means that Cl minus must change into Cl2. Okay, if it is oxidized means, okay, you are going to lose electron. Okay, so it means it must change into this. Okay, if it is changing into this, okay, Cl minus changing to that, it means this equation must be negative 1.36. Okay, this is positive. So if I have MnO4 minus, okay, then MnO4 minus is 1.64. Okay, if depends on which one you want to use. Let's say I use the 1.52. Okay, it's positive. So when I add, okay, when I add, I will get a positive E value. Okay, if I get a positive E value, the answer is yes, something like that. Okay, so you use, okay, whichever method that you are comfortable with. Okay, let's see again. Yeah, okay, another question, checkpoint number 3. So why, okay, bromine, okay, can oxidize an aqueous solution of iodide ion? Remember last time, okay, you learned about, okay, CBI, okay, Cl, Br, and I. Cl is more reactive. It can actually displace the Br from its solution and so on. From now on, you no need to memorize anything. You can use all the E value. Okay, so the answer here they say that why Br2, okay, why Br2 can oxidize a solution of iodide ion. Okay, so oxidize means I minus, okay, I am changing the I minus into I2. Okay, so this is going to be the equation. So my my question over here is, can Br2, okay, can Br2 change this into this? So it means that it must be, I want to change this to here, okay? It means if I use the E value, yeah, this is plus 0.54. If I use Br2, okay, you see Br2 plus 2 electron to become 2 Br minus, okay, this one is going to be 1.07. Okay, and if I add these two equations, yeah, if I want to add these two equations, remember this one is going to the right. Okay, this, okay, supposed to be, okay, going to the left. Okay, so this one, if you want to identify can it oxidize or not, okay, you just need to, okay, use the two method. Okay, if it is going to be, you can see here, this is more positive. Okay, if this is more positive, okay, first of all, if you, sorry, let me rewrite this again. Okay, if you want to identify that, okay, if you write down Br2 plus 2 electron, they will give you 2 Br minus. That is going to be positive 1.07. And then you want to write down for I, yeah, so that's going to be I2 plus 2 electron, okay, to give you 2I minus. This is going to be 0.54. So if I want to find out, can this Br2, this is going to be strong oxidizing agent. Okay, you can see this is more positive, this is less positive. Okay, remember how you rearrange them. Okay, this one can oxidize, okay, the strong reducing agent. Okay, so you can see they can. Okay, the answer is can. Okay, so this is how you use the is more positive. Okay, and then this one is going to go to the left. So you will have 1.07. Okay, you add with negative 0.54, you will get a positive value. Okay. Okay, sir, how do you know which one is SOA, which one is going to be SRA? Then come back over here again. Okay, good question. Okay, you will come back. Okay, you arrange them. Okay, like 0 over here. The one 0.36, you rearrange. Okay, you rearrange. More positive over here, more negative over here. So the one on the equation, if you look at the standard reduction equation, the one on the left is going to be your SOA. The one on the here. And the one that is going to be on the right is going to be your SRA, this one. That is how you identify. So here you can see in this table, you have so many examples. Okay, but if you can just compare with two only, no problem. You can see more positive, right? Less positive. If I arrange 0, then I have 0.77, 1.36. Okay, so you can see this is 1.36. It's okay. I rearrange, and this is automatically SOA. Okay, on my left hand top, and this is automatically SRA. Okay, this is how you can identify. Okay, hopefully this answers the question. Yeah, the same thing also. Okay, how do you identify which one is SOA or which one is SRA? Okay, SOA. Okay, the one that has the E value, which is going to be most positive, and they must be at the left. Okay, at the left. Okay, so this one you come back to this. Okay, this slide. Now, so if you go on, okay, if you go on, okay, I was talking about, okay, this, okay, you can see, okay, if you want to tell, okay, using calculation, I want to find out also can, calculation also can, you can use the equation also, no problem, okay, you can see more positive, less positive, this is automatically SOA, this is going to be SRA, yeah. So you can see how do you explain the answer just now, can, yeah. Can it oxidize? Yes, okay, can. So if it is can, you explain why, okay, because, okay, this is going to be more positive. You just tell more positive E value, okay, and then this is going to be less positive. They are going to be more, they will go to the right. It means they are having the tendency to accept electron, okay, and this one will have tendency to lose electron, then the reaction can happen. Okay, you read through. Yeah, you can read through and then you can explain. And why, okay, this one doesn't react. So you just explain why. Okay, you can explain in 2 points of view. Okay, but whatever way that you explain, you must explain whether, okay, the E value, okay, if you're using the calculation method, then you must mention that the total E value is going to give you positive, then it's feasible. Okay, but if you are explaining in terms of equations, okay, then you must tell, okay, which one is possible to happen, okay, which one not possible to happen. You can just go through this example, how they have explained, okay, you can just get an idea how to explain, okay, but the important thing is to get the concept right first. Yeah, so if you look at this summary for the first part, okay, these are the things that we have done. Okay, we have done all this hydrogen electrode. Okay, we have done, okay, you can see all these are taken from your syllabus. Yeah, so we need to find out the direction of electron flow, done, and we can use the E value to determine the feasibility of the reaction. It means that if your E value is positive, then the reaction is feasible. Yeah, so deduce from E values, okay, relative reactivity of elements, okay, oxidizing agent and so on. So that is going to be when you have the 0 and then you have more positive and then less positive, which is negative. Okay, if you look at the equation, and then the one on the left and the one at the top is known as SOA, strong oxidizing agent. The one at the right bottom, they are going to be strong reducing agent. So V1, okay, SOA combined with SRA, they are going to give you a feasible reaction. Yeah, that is going to be another thing you can memorize. Okay, and of course this one you should know how to write down the redox reaction using relevant half equation. You balance the electrons and you cancel the electrons. Okay, so you can see how I have shown you all these examples just now. All these are balancing. Yeah, so how to balance and then cancel the electrons. Okay, make sure you know how to do that. Okay, so now, okay, we will go to part 2. Okay, the part 2 is calculation part. Okay, this is going to be known as Nerst equation. Yeah, so we have learned the E value. Okay, they happen. Okay, we can calculate under standard condition. What is standard condition? Yeah, 25 degrees Celsius, 1 atmospheric pressure, and 1 mole per dm cube. Okay, but not all the time. Okay, you are going to have 1 mole per dm cube. Okay, so can we still calculate under non-standard condition? The answer is depends. Okay, the answer is depends. If you look at, we have already learned about LCP. Okay, Le Chatelier's principle. Yeah, so if you look at this LCP, okay, if let's say for example it's supposed to be, we supposed to have, okay, 1 mole per dm cube, but let's say the zinc 2 plus is greater than 1 mole per dm cube. Okay, you use the LCP. What is the LCP? If the concentration is high, I want to eliminate the concentration. I must make the concentration less. How do I make the concentration less? By moving or removing the zinc 2 plus. Okay, it means the position is going to be shifted to the right. So when this is happening under non-standard condition, what will happen? You can still hear me. Okay, I think my connection is breaking. Okay, anyway, okay, let me explain again. Yeah, if you have, okay, if you have a let's say for example, zinc 2 plus is going to be more. Okay, if zinc 2 plus is more, okay, and then, okay, what I am expecting, okay, LCP. According to LCP, I am expecting the position of the equilibrium to be shifted to the right. So it means that if it is shifted to the right, it means the value, the E value is supposed to become more positive. Okay, so if you have a negative 0.76, what do you expect? I expect the value to become maybe 0.60. Okay, maybe negative 0.5. Okay, you can see here. Okay, that's why, okay, the more to the right, you will become more positive. Yes, explanation. If you have less than 1, okay, less than 1, okay, what do you expect? Okay, according to LCP, if it is less, okay, you need to make sure, okay, the concentration to be increased, okay, by shifting the position of the equilibrium, okay, to the left. Okay, you can shift this to the left, okay, and what it will do, okay, it will make, because you're going to the left, okay, it will make the E value to become more negative, okay. So earlier, now you have negative 0.76, you will have greater negative. Probably, you can see here, they say probably negative 0.80, yeah, because it's going to the left. Okay, because according to my teaching, remember, if you go to the right, yeah, because more positive, right? Okay. If you go to the left, yeah, because you become less positive or negative. Okay, you can remember that way. Okay, you can use this. Okay, you can see here, if you have two different ions present in the half cell, you have to consider both ions. Okay, so here, okay, if I'm trying to say, I think same concept. Okay, if this one Fe3 plus is increased, okay, what I need to do, I need to remove the Fe3 plus. Then you go to the right. So if you go to the right, then you will become more positive than 0.77. Okay, and so on. Okay, you can read. But okay, what will happen if you try to increase both of them? Fe2 plus and Fe3 plus also increase. Okay, what will happen? Okay, then you consider both. Okay, how do we consider both? Yeah, Fe2 plus, you need to decrease. You have to go to the left. Fe3 plus, I need to increase. I need to decrease also. Yeah, so I will go here. Then they will cancel out each other. So that is why they say that this effect may cancel each other out. Yeah. So this one you can read. Okay, it's still the same concept. But what is important over here is, okay, if you are talking about non-standard condition, then the LCP will start to come in. Okay, so you use, okay, the LCP and find out whether they are going to go to the right or whether they are going to the left. If they go to the right, then they will become more positive. If they go to the left, then they will become more negative. Okay, I think better if I write it over here, they will become more negative. Okay, so this is something that you can memorize. Okay, something that you can remember. Yeah, so here, okay, how to predict? Can we predict under all conditions? Not really. Okay, you cannot predict them under all conditions. You can only do a valid prediction whether, okay, this cell, okay, they will work. Okay, I can expect that this is going to give me this. I can only predict, okay, if the E standard difference is greater than 0.30. Yeah, it is going to become non-valid, or you cannot predict if the difference of E standard is less than 0.30. I'll give you what is meant by that. You can see these two. Okay, if let's say one of this Cl2 or Fe3 plus, they are not at 1 mole per dm cube. Okay, and they ask you to predict. I can use the same method. Like, what is the method? More positive, less positive, it will go here, then it will go here. This is how you do in the previous part, right? So we can find out what will happen. Okay, but this is going to be under non-standard condition. Okay, what you need to do first is you find the difference between them. Okay, you find the difference between them, you just can minus, yeah, 1.36 and 0.77. If the difference, okay, you see the difference is 0.59. If the difference is greater than 0.30, no problem. You can use your prediction. What is your prediction? This one will go to the right, this one will go to the left. And then if it is right, 1.36, this is left, negative 0.77. I can find what is my E value. Okay, so most likely the prediction will be correct. Okay, but the prediction will not be correct if you have this situation. You see, if any of this, okay, if any of this, the concentration is no longer 1, okay, if I want to predict, you need to first check. Okay, you check. You only check when they are not in when they are not in standard condition. Yeah, most of the time it will be standard. Okay, But if they say the concentration is no longer 1, then you need to check first. You find the difference, and when you find the difference, 0.16, what is your conclusion? You do not need to do anything. You can say, whatever that I predict will not be accurate. Why? Because the difference is smaller than 0.30. So it will be unexpected outcome. So you cannot calculate or predict. Okay, this is going to be the situation under non-standard condition. Yeah. So what we can do here, okay, you can see here, this is checkpoint number 4. Okay, they say that, okay, this half cell have E value 1.33. Suggest what will happen to the E value when this one is increased. Let's try, yeah. According to LCP, when this one is increased, okay, I need to decrease this, so position will move to the right. It will become more positive. So what will happen? Greater than 1.33. If this one is decreased, okay, let's try. Okay, when this H plus is decreased, I need to increase this back. So go to the left. So when it is going to the left, it will become more negative. Okay, it will become smaller than 1.33. Okay, and then what happens to CR3 plus if it is increased? CR3 plus, when it's increased, you need to decrease it back. So you move to the left. Okay, so it will become more negative. Okay, so it will become less than 1.33. Yeah, so they will ask you, okay, what effect would each of these concentration would have on the strength of the this solution as an oxidizing agent? Let's see. Okay, when I have this, okay, this one is going to the right. Okay, when this one is decreased, then it's going to go to the left, and this one will become going to the left. Okay, so here I can find out, okay, from this equation, I can find out whether they are going to become a very good oxidizing agent or not a very good oxidizing agent. How do I find out? What is oxidizing agent? Oxidizing agent is something that will oxidize others, but they themselves will get reduced. What is reduced? Reduced means gain of electron. So I want to see which one can gain electron easily. There is only one that can gain electron easily, which is under this condition, because this one gain electron when they go to the right. Okay, so you can see only this one. Okay, you see stronger oxidizing agent. But for these two, they are going to become weaker oxidizing agent. This one we have already learned. Yeah. So what condition would you use to make a solution, this solution and a strong oxidizing agent? You want to make it as a very strong oxidizing agent, means I need to change everything to go to the right. Okay, it means I must gain electron. How to make sure that everything gains electron? You increase the concentration of this, then they will go to the right. You increase the concentration of this, they will go to the right, according to LCP. You decrease this concentration, and then they will go to the right. Okay, so that's why you can see high, high, low. Okay, now, so use LCP, you can just use LCP. Yeah, please actually go through this example. Yeah, but today, okay, let's actually learn about this. Okay, Nerst equation. Now, according to this Nerst equation, okay, Nerst equation is used, okay, to predict, okay, the E value, okay, when you have different concentration. According to this one you can go through again also, this graph, okay. This graph is just telling us that, okay, the E value, okay, at here is going to be under standard condition is 0.46. But if you tabulate a data, if you actually plot a graph, okay, you can see that when the concentration, okay, concentration of what? Ag plus, when Ag plus increases, okay, we know that when Ag plus increases, according to LCP, I need to decrease the Ag plus. So the position will go to the right. It means this E value is going to become more positive, right? So here, okay, you can see all this. When concentration is increasing, okay, the E value is increasing. So it is showing you, okay, in form of graph, okay. But okay, what is important here is going to be the equation. Now the equation, okay, this one is all these can be found in your textbook. Okay, the E value, okay, under non-standard condition is calculated by taking the standard value, okay, you add with, this is a gas constant 8.31, okay, and then this is temperature in Kelvin. This is going to be number of moles of electrons that we are dealing with. and this is going to be the Faraday constant 96500. Ln, okay, natural log, okay, and then oxidized form and reduced form, okay. A lot of you will get confused. What is oxidized form? What is reduced form? To avoid this confusion, remember this. Oxidized form, do remember your standard, the way we write is X plus electron to give you X, right? So we write like this. Always remember oxidized form is on the left. Okay, oxidized form is on the left. Reduced form is going to be on the right. You can remember that. Yeah. Now they have simplified this, okay, into this equation. Yeah. You can read this, okay. But okay, if I put in this manner, if I simplify everything, this is going to be the equation that you need to memorize. Okay, you need to know this equation. Do remember this is Ln. Yeah, natural log. Okay, but okay, in your textbook they have simplified. Why? Because this is a constant, okay, and this is a constant, okay, and P is going to be, if it is going to be standard condition, then it's always 298. Okay, so they have changed this, and then natural log, no, they change it into log 10. If you want, you can actually use this formula. Okay, but okay, please remember in your text, in your syllabus, this formula is not given. This is only recommended by your textbook. Okay, the formula in the syllabus is this. Okay, this is the formula. Okay, and you can have a look. Okay, it's going to be 0.059 divided by Z and then log. Okay, so you can see it's similar. Okay, but there is one missing over here, which is going to be reduced species. Now, why they didn't put the reduced form over here? Because they are taking into consideration this equation only. Okay, if you take this consideration, okay, remember I told you oxidized is the left, so they take the Cu2 plus. Okay, Cu2 plus is on the left, and then this is going to be solid. It means they this one they will not include. Okay, now this formula is going to be valid only if you are using this equation. Okay, but do remember in your syllabus there is another equation that they want you to know also, which is going to be involving ions. Okay, Fe2 plus and Fe3 plus. It means that you need to know that the oxidized species, if I want to use for this, the oxidized species is going to be on the left, Fe3 plus over here, and the one reduced species is Fe2 plus at the bottom. Okay, please remember that. Okay, so please remember this. Okay, so this is what, okay, if you want to remember this, okay, fine. Okay, but make sure not all the time. Okay, not all the time. Okay, there is also a reduced form here. Okay, but now it's going to be log. Okay, we will use log. Now, next, what is Z? Please remember the number of moles of electrons that are involved. Okay, 3 more minutes. Okay, I think we need to continue next lesson. Yeah. So anyway, you can see here. Okay, if I want to find the value of electrode potential, okay, for this, okay, you see what you need to find out. Okay, this is a non-standard condition. The moment you see this, a non-standard condition, then you need to use Nerst equation. Okay, so you see whether you want to use this or this. Okay, I will just use this one, but do remember this one must be reduced form here. Okay, but this one doesn't matter because Ni2 plus and Ni is going to be constant. Okay, so no need to put anything over there. So if I want to write down, okay, the E value, I want to calculate E equals to, okay, you can see, I think to save time, you can just use the solution here. E equals to, okay, this value is already given. Okay, you have this value. This, okay, you put over there, log 10 and I plus 2 plus, it's already given. Why divided by 2? Because Ni2 plus 2 electron to give me Ni, 2 moles of electron. So that is going to be 2. The Z is going to become 2. And you calculate and you will get a value which is negative 0.24. Now, what can you say about this value, negative 0.24? This is also important. Ni2 plus 2 electron under standard condition is going to be negative 0.25. But now Ni2 plus is having more than 1. It means the concentration of Ni2 plus is greater. If this one is greater, like what we say learned earlier, according to LCP, you need to decrease the concentration, so you move to the right. So what happens? You are going to get a more positive value. Okay. So you can see when you calculate, you get negative 0.24, which is valid. Okay, which is going to be like what we are expecting. Okay, because it's supposed to go to the right. Yeah. So you can just apply all this that I taught you. Okay. This one also you can do. Okay, the same. Okay, you can calculate accordingly. Okay, even if I don't go through also, okay, the marking key is there. Okay, it's all taken from your textbook. Yeah, so if you want to calculate, you can calculate. If I want to predict also, I can predict. Okay, you see copper 2 plus 2 electron to become copper. You can see copper 2 plus is less than 1. If less than 1, it means it's supposed to go to the left. If earlier 0.34, okay, what do I expect? I am expecting the value to become less than 0.34. And you can see the value that you calculate is also less than 0.34. This is how you apply. Yeah, how to apply. Now, predicting feasibility, we will do it next lesson. Okay, I think this one we can still leave it for next lesson. Okay, but what I want you to remember, okay, over here is, okay, you see, if I take the summary over here, the summary is going to be, you need to know how to apply the Nerst equation. Yeah, so Nerst equation you need to apply, but what I want you to know is the oxidized species must be on the left. The reduced species must be on your right. Okay, and then this one we will cover next lesson. Okay, and one more thing. Okay, I think to summarize whatever things that I taught you, if you have, okay, if you have this E values, okay, if this one is going to be 0, if you rearrange them, this one is more positive, if this one is more negative. What can you say? You can say, like, for example, if this one is X plus electron to give me X, okay, I can say that this is going to be SOA, okay, strong oxidizing agent. If let's say I have Y plus E to become Y over here, which is negative, okay, I can say that this is going to be SRA. And SOA can really react with SRA. Yeah, so this one is feasible. Okay, so you can actually learn about that. Okay, but of course, there is another major part that we need to do, okay, for predicting feasibility, but I don't want to rush it now. Yeah, so you can actually also go through, okay, it's just application of formula, okay, but I think we can do it during our revision on Thursday. Okay, anyway, guys, here, okay, you do need to complete the reflection for today. Yeah, please complete the reflection. It's all done for today. Okay, please write down. Okay, we will go through everything. Okay, everything that we learn under electrochemistry on this Thursday. So everything joined together plus the part that we couldn't cover today. Yeah, that's all from me today. Okay, bye guys. See you.
Thank you, Mr. Gupta.